My name is Donald Simmons. I'm a senior engineering analyst at MSC Software, and we're going to be talking here this morning about solving complex contact problems in Marc. So this is just the table of contents. We'll be doing an overview of how contact is useful, how it works in Marc, some troubleshooting issues when you're dealing with contact, and then 2 demonstration problems. So we're going to start with a general look at contact. Now, contact is very useful for engineering applications because it allows you to have load transfer and interaction between multiple components or different regions of the same component. And contact is a real-world thing. It's necessary to handle because it's the most accurate way to model many real-world problems. It says the applications are numerous in the automotive, aerospace, energy, biomedical, and manufacturing industries, and we can see some example problems running at the bottom of the screen. So at the end of this webinar, I'm going to be presenting the results of 2 complicated contact projects I performed. One of them is biomedical, which is going to be the crimping and expansion of an arterial stent, and the other one was for the oil industry. It's an industrial application, setting up a casing seal and running it through thermal and pressure cycling. So contact lets you model complex nonlinear boundary conditions. Its capabilities in Marc are that you can use it with nonlinear materials. You can use it in large strain and deformation problems. Self-contact is, you can use self-contact in a contact body. That means you can have a single contact body that can touch itself, its own elements. And that's very common when you're dealing, say, with rubber seals and rubber gaskets. It deals with changing contact conditions. In many contact problems, the area that contact can occur may change widely over the entire simulation. We have several models in which to handle friction, and we can even calculate friction-generated heating, say, between 2 bodies in contact with each other. And Marc uses several numerical solvers to solve for contact detection and the forces between it. These solvers may work better for one problem than the other. This is a more advanced concept. We're not going to go into any detail in the webinar today, but there are various different mathematics. These are an example of the various different mathematical procedures available. Now, contact. There are 3 main procedures for contact detection in Marc. The earliest and frankly the least capable is the node-to-node. This was the earliest form of contact, and it uses what we call gap elements between the nodes in the 2 contact bodies. The node-to-node contact required that the mesh between the 2 bodies in contact to be in exact alignment with each other. Where there was a node in one body, there had to be a node exactly opposite it in the other. This is so we could set up what's called a C-gap element between the 2 nodes that monitors the contact. As you might expect, this took a lot of work to set up properly, and it was only good for small deformation problems. A much more capable and robust contact algorithm came along about 15-20 years ago now, called node-to-segment contact. It allowed contact between general FE elements. You could easily have solid elements contacting other solids, shells contacting other shells, and combinations thereof. You could use it for small and large deformation problems. It allows for nonlinear deformations. The big disadvantage of node-to-segment contact is it can be mesh sensitive. You can get, it works best when the mesh on both sides of the problem is relatively refined and roughly the same mesh densities on both sides. Node-to-segment contact can lead to spotty contact between the two bodies. As we can see in this example here, where we have a bolt going through a solid plate. Here we have the stress calculated, and you can see it's not completely smooth. The stress calculated here is not completely smooth. A more advanced contact Marc has now is called segment-to-segment contact. Again, you can use general finite elements for it, and it works for small and large displacement problems. It is broadly mesh insensitive compared to node to segment. In certain classes of problems, you can easily get much smoother contacts and much smoother results than you would find for node to segment. So we're going to talk about a little more in detail about exactly how contact works in Marc. So in a general finite element problem, a finite element can communicate, say, and pass loads and stress and displacement information to only the other elements that it is attached to via nodes. This means that in a problem such as you see here, if a closing force is applied on this model, these elements here, because they are not connected through nodes, they will end up simply passing right through each other. And so the problem is not physically realistic. Again, but you cannot attach these together initially because there's an initial gap between them. So this is an example of why contact is necessary to model. Sometimes now even can be necessary to model even moderately difficult real world physical situations. So to use contact in Marc, you have to place the elements in question together in what's called contact bodies. So in this example here of this flange, we can see we have each of the L sides here is a contact body, and we have different bodies for the bolts running through them. Now, in this example, they've selected all of the nodes in each of these bodies here to form our contact body. And one contact body can come into contact and looks to detect other contact bodies. The contact between them, that is, which body can come into contact with the others, is defined by what we call a contact table or contact pairs. A contact table is a spreadsheet-like assembly where you can select what bodies come into contact with which others. Contact pairs allow you to choose on a one-to-one basis what contact bodies react with what others. Contact tables, contact pairs are relatively more recent. They can be more straightforward if you have many contact bodies in your model. Contact tables can be quite useful if there are a small number. It can be easier to keep track of a small number in a contact table. Now, contact is made possible in Marc between solid elements, shells, beams, the edges of shells and solids, and combinations thereof. So solid elements can look for contact against other solids, or you can have solids contacting shells, beams contacting solids, so say the edges of shells contacting solids, or other shells. So it's not necessary in Marc to select, say, outer edges, surfaces, or a small subset of elements in order to set up your contact body. In fact, we recommend you don't try to select small subsets. In this example, they've selected the entire body here into all of the elements, say, in each section into the contact body. Like, we don't expect these elements here to come into contact with anything, but you don't see any kind of great penalty in performance by including them in the contact body. Setting up a contact body this way is quick and simple, and you can run into more trouble trying to select as few elements as you think you can get away with, rather than selecting all of the elements in the model. Again, in Marc, it's not necessary to define complicated master-slave relationships between the contact bodies in question. And Marc defaults to and if you have more than one contact body, the Marc defaults to checking all of the bodies against all of the other bodies. Again, that can be quite simple for models with just a few number of contact bodies. In numbers with large numbers of contacts, you'll probably want to use, say, a contact table or contact pairs to set up specifically which bodies can come into contact with which other bodies. So Marc contact, it can handle changing relative node locations. That is, it can handle small and large sliding problems, especially here in something like a rubber gasket, where the surfaces in contact can change drastically over the entire simulation, from, say, no contact to virtually the entire outer or inner surface of the gasket. Contact will calculate the normal forces and stresses between the bodies or surfaces in contact. There are multiple friction models that can be used, and friction is optional. You don't have to use it if you don't think it's necessary. Contact calculates the transfer of force between the contacting bodies, and it will continually calculate the contact area in relative sliding problems. So the problem may go from small contact areas to very large ones and back again. Contact will handle geometric and material nonlinearities. And we have an option called automatic remeshing, where the mesh can be automatically recalculated due to changing conditions in the problem. Say, a coarsely meshed region of your model may be automatically redefined, remeshed into a finer mesh once contact takes place somewhere on that surface. And contact will work for multi-physics problems. For example, you can have thermal contact problems where you have heat transfer between two surfaces that come into contact. So that's a combined structural thermal analysis. You can do handle friction heating, electrostatic, and other options. Also, we have a glued contact, which allows the joining together of individually meshed parts. In this example here, we have two solid bodies, one meshed with hex elements and one with tet elements. But we need this to act as a single solid piece, so we can define a glued contact where they meet. So when forces are applied on the body, the two bodies move as one, so that continuity of deformation and stress is enforced through this boundary. Now, this can greatly simplify the meshing of complex geometry. If you have several bodies touching each other, instead of trying to get a congruent mesh between the two parts, which can be very difficult for complicated geometry, you can put an individual mesh in each body and then simply glue them together. The glue can also break for a user-defined force. Say, this can start out glued, but once the force applied, a separation force applied, is big enough, you can break the glue so the two bodies now move independently of each other. Again, this can be a real time saver. Okay, so we're going to take a look at some issues and troubleshooting matters when you're working with trying to solve contact problems. As in any FE analysis, your solution time and your stability issues of your model increase as your model gets larger and larger. So as always, you want to simplify your problem wherever possible. Say, you may want to look, if you don't think, if friction isn't really necessary, you may want to run your problem without it. You can look at reducing the size of your problem by using submodels. Maybe you just need to look at create a submodel just to look at a particular contact situation. And you can always look to try and reduce the problem using symmetry or convert it into a two-dimensional problem, say an axisymmetric or a plane stress or plane strain problem. Here in this bottom example here, they've simply taken a cross-section of the seal, probably as a plane strain problem, to calculate the contact, to look at how the contact works. Now, if one contact body in your problem is very much stiffer than the others, it can be considered rigid. Say, in this example here with a rubber seal, this is a rubber seal in blue, which is a deformable body, but we've defined what's called a rigid body here as a curve. and say this curve can be moved via displacements of forces that come into contact and compress the gasket. In this example here, we're simply interested in looking at the stresses and strains in the gasket, not in the body that's doing the contacting. So in this case, they've created a rigid body to do so. Now, by its name, a rigid body is infinitely rigid. It undergoes no displacements whatsoever. And because of that, there is no stress or strain created on the rigid body. But that's okay for many applications. Say, when you're closing a seal here, if the seal is exerting negligible force on the other part, so you're not interested in the stress and strain on it. Also, if you're doing models where, say, one component is very much stiffer than the other, that can lead to stability issues. Using a rigid body here eliminates those issues. And Marc rigid bodies can be set to apply prescribed loads or prescribed displacements. They are easy to set up, and they're easy to use to apply specific loads onto the more flexible rest of the model. Again, there's no stress results are obtained on the rigid part, but you can also glue rigid bodies to deformable bodies. And that can be a very useful means to manipulate the rigid body to control the response of the deformable body in the simulation. Talking again, so the default contact checking algorithm in Marc is the node to segment procedure. And as we've mentioned before, it's robust, but it can have spotty contact over larger areas. That's especially if you have two bodies of the same stiffness that, say, come into contact over a large area. With node to segment, you can sometimes have a few nodes between the two bodies may come into contact and bear the brunt of the contact rather than the entire face picking up the contact. In situations like that, the checking contact order of the bodies is often important. You may have to specify which body is checked first against which other body. Marc has a good automatic checking procedure that takes various properties of your model into account. That usually works quite well in determining which contact body should be most efficiently check the other. It takes into account the mesh density of the two bodies and the relative stiffness of the two bodies. Again, the revised segment-to-segment routine can have improved accuracy and performance over node-to-segment. And it depends on the problem in question. But segment-to-segment does eliminate issues with contact search order based on the mathematics of how it works. And it's very simple. You can switch between node-to-segment and segment-to-segment in Marc just from a single menu. You can simply switch over from one to the other and check out which one may work better for the problem in question. It requires no other changes to your model. And so some general guidelines here for putting together contact models. Again, in your contact region, you generally want to refine your mesh in the contact region and have roughly the same mesh density on each side. Again, it's generally better to avoid having fine meshes coming into contact with coarse meshes. Small amounts of friction on your problem can add stability. Say, in a model like this where a bolt may be completely free-floating, it may rely only on contact with other parts to keep it stabilized in space. In situations like this, a little friction between parts can help stabilize your problem. It keeps the bolt where it should be, and it removes the possibility of the bolt sliding without friction right out of the hole and away. Now, if you want to avoid, in your initial geometry of the problem, you want to avoid having large gaps or overlaps between bodies in contact, especially if they're in contact at the very start of the simulation. If bodies overlap each other at the start of a simulation, Marc may be unable to determine the contact on them at all. And again, if there are large gaps between bodies that should initially be in contact, that can be difficult to resolve as well. So you usually want to check that your geometry is as clean as possible. If you're having problems resolving your contacts initially, a good check is to initially set all of your touching contacts to glued and then simply run the simulation for a single step. That can be a check to see that can allow you to very quickly check and look at your results to see what contacts are working and what contacts are not. And if contacts are not working, there are various contact parameters that can be user adjusted between the contact bodies. Say, these contact parameters can be adjusted generally for the entire problem, or they can be adjusted specifically just for a particular contact pair. Say, if you only have problems with one specific pair, you can adjust the contact parameters for just that pair only. Contact parameters can also be adjusted between simulation load steps, and that can be necessary if the simulation, if the loading problems or contact situation of the simulation changes drastically through from beginning to end of the simulation, and we'll see an example of that coming up shortly. Okay. So I'm going to take a look at our first demonstration problem here. This is a casing hanger. This is an analysis I did a few years back. It's a rubber seal that's placed first under a preload and then under thermal and pressure cycling. So here in our geometry, we see this is a cross section of a circular geometry. We have two sections of a casing on either side, and the seal unit fits in between the two sides of the casing. How it worked is we have an elastomer seal that's between two plates. We have studs running through it, and the studs are tightened down with nuts. So this compresses the seal between the two plates. And as the seal is compressed, it bulges out on either side and makes contact with the casing on either side. So a pre-tension load is put on by screwing down these studs, so it forms a seal. So the elastomer forms a seal on both sides of the casing. Now this seal had to go through thermal and pressure cycling. So the point of the analysis was to make sure that there was sufficient contact pressure on both sides of the seal throughout the cycling, that the seal would work throughout the entire simulation. So here's the FE model that was created for this analysis. So it wasn't necessary to do the entire 360-degree seal. We have here a segment that's about 49 degrees long. I chose this amount because here we have along the section of the seal, we have studs and pins running through it. Aside in this submodel here, we have an entire stud, an entire pin, and then say we have half a stud here and half a pin here. So we would put symmetric boundary conditions along these two cut faces here. So this segment would simulate all of the physical processes and reactions we would expect to see in the entire 360-degree seal. So in this model here in blue, we have the elastomer seal itself. It's clamped between the steel compression plates on the top and the bottom. And the studs and pins run through holes in the seal. So the seal model here will be in touch and contact with 8 components in total. We have the top and bottom compression plates, the studs and pins running through it, and the casings, they were modeled as rigid surfaces. They're not shown in this model for clarity, but we have a rigid surface on each side. Again, we weren't interested in the stresses on the casing. Besides, the casings were so thick, the forces exerted by the rubber seal should be negligible against them. So we could simply use them as rigid surfaces and simplify our problem. So the seal here is completely free-floating. The only boundary conditions that constrain it are the contacts set up on all sides of it. We created a material model for this seal material using material data that had been provided by the customer. We created a neo-Hookean material model from tension and other data provided. There's actually tools in Marc to do this automatically if you can provide Marc with physical test data. We knew the material became softer as the temperature increased, so we handled that by creating a temperature-dependent bulk modulus for the material. The bulk modulus is a measure of how much force is required to compress the material. And we set up a temperature-dependent coefficient of thermal expansion for the material as well. We use a standard elastic steel model for the rest of the hanger components, but we use an elastic plastic material model for the studs and pins that are used to compress the seal, so that they would yield if they reached 105 KSI. Okay. So here are some results from the initial loading of the seal. So we screwed down the studs so that the seal is initially put under, compression. So we it was a few thousand pounds of tension in all of the studs. So this is showing the contact force on the seal. You can see that we have a nice, this is the pressure applied on the casing. You can see we have a nice even contact pressure result here. And you can see the contact pressure on top of the seal. This is from the compression plate on top of the seal. Here we have an image of the compression plate, and here you can see where the nuts from the nuts on the studs make contact with the compression plate. So the contact runs through the nuts into the compression plate and forces the compression plate down when the preload is applied, and the compression plate then compresses the seal itself. So now the temperature of the seal was to be cycled from 70 degrees Fahrenheit to 250 Fahrenheit, and there was to be pressure cycling. Pressure was going to be applied on the top and bottom compression plates as well. So we can see some results here that were calculated. We have here the pressure of the seal on the casing during the load cycling procedure and the tension in the studs. So here we can see that this is the initial pre-tension. We can see there's a load of about 600 psi on the seal applied, and that goes up that goes up a lot as the temperature. Here is at 250 degrees Fahrenheit. The force applied in the casing is now nearly 5,000 psi. But we found when the temperature and pressure go back to standards, if you drop the pressure again to 70, the contact pressure between the seal and the casing fell to essentially zero. And while it picks up again if the temperature of the pressure is cycled, when that's removed, we found the pressure went down to zero again. And we see the same thing in the tension in the studs. The studs were initially under nearly 9,000 pounds of pressure, which goes up as the temperature increases. But as the temperature fell, again back to normal, the tension in the stud fell to zero or nearly so. So this is indicating we're having a problem. The casing hanger is not maintaining a sufficient seal after the thermal cycling is taking place. So at time equals 1 in the simulation, we found there's positive pressure on the casing and tension in the studs. But at time equals 5, the pressure had fallen to 0 and the tension has been greatly reduced. What we found that at the maximum temperature applied, the seal expanded sufficiently, there was sufficient thermal expansion of the seal to plastically deform the studs. The stress in the studs rose above the yield of the material, of the stud material. So the studs were actually being physically stretched. So when the temperature cycled back to 70 degrees, there wasn't enough pre-tension in the seal anymore to maintain pressure because the studs were physically stretched. So the customer would have to look at either redesigning the seal or perhaps switching the elastomer material to something with a lower thermal expansion coefficient. So we have a second demonstration problem. This is a medical stent that's placed under compression and expansion. So this is a model for an arterial stent. It's a thin wire cage, and these are inserted inside blood vessels to help keep blood vessels open. This stent we see here is actually under an inch long. So this is actually a very small model with very fine finite elements making it up. So this stent, first it has to be crimped, it has to be compressed in order to be small enough to be inserted into the blood vessel, and then it's expanded with a balloon in its center into the walls of the blood vessel to hold it up. Now, fatigue and stress analysis is critical for this analysis because this is a component that has to last for years inside the human body without any issues involved with its breaking. So the stent here was modeled as an elastic plastic material, again using data provided by the customer, and with work hardening, added into the material model. The blood vessel itself was a simple elastic plastic model. So to create this model, here we're looking at the stent end on. The stent is surrounded by 24 rigid surfaces. These are the surfaces used, called the crimping surfaces, to compress the stent. All of these surfaces simultaneously move radially inwards towards the center, and they compress the stent between them. After the stent is fully compressed, the crimping surfaces would then pull back, allowing the stent to recoil. Here in the center of the stent is another rigid surface that's the catheter, the balloon used to expand it. This, after the catheter is radially expanded, that is, it's simply made radially larger, which Marc can do, and this pushes the stent outwards and expands it into the blood vessel. The catheter is then reduced in size, allowing the stent to recoil into its final diameter. So here we have images of the stent edge-on during its entire procedure. We have the start here with the crimping surfaces, the catheter in the center. At full crimp, you can see that all the crimping surfaces have moved in to compress the stent between them, with the catheter at its center. When the crimp is released, all of these crimping surfaces have to be pulled back. And you can see that the stent has recoiled somewhat. It's slightly larger than it was at the full crimp. And again, that's a real physical property that we have to be sure we accurately model. The crimp releasing can be tricky because as these surfaces come back, they all must release from the surface of the stent. And because the forces involved in this are so low, I found that when I was doing the simulations that usually required some manual intervention in the contact parameters in my pod to assure we got good separation. Because sometimes single nodes might get hung up on the crimping surface, and that would lead to the stent being pulled unrealistically. After the crimp is released, the catheter is expanded. You can see the crimping surface is still here, and the catheter is pushed past those to expand the stent into its full size. Between these two steps, the crimping surfaces have to be removed. The contact between the stent and the crimping surfaces has to be removed entirely, because the stent has to be able to push past the crimping surfaces now as if they weren't there for the expansion procedure. Then the catheter is released. The catheter is pulled back, and the stent again recoils slightly into its final size. So here are some images of the stent and the blood vessel when the stent has been fully expanded. Now, only two deformable bodies were necessary for this problem. The entire stent is in one deformable body, the entire blood vessel in the other. And even though there's two deformable bodies, but here in this image with the stent removed, you can see how the stent has made contact with the blood vessel at multiple locations along the entire length. But you only needed to find the two contact bodies to pick up all of these individual points of contact. And you can see here on the outer surface of the blood vessel how the blood vessel is pushed outwards where the stent has pushed into it. So the stent is now supporting the blood vessel. So here are some images of the stent when it's fully compressed. We can see that all of the various loops of the stent have come into self-contact with each other. Again, the stent is a single body, but it's able to keep contract of all of these, probably a couple of dozen of regions of self-contact along its entire length. In this plot here, we have the plastic strain on the stent plotted. And as you might expect, this plastic strain is highest on the inside and then the outside of all of these loops. Here's an image of the stent fully expanded. So at the full expansion, all of those loops have pulled away from each other now. I think the stent is now no longer makes any contact with itself, just with the blood vessel. And again, we can see the plastic strain at the inside and the outside of all of these loops here. So for this stent problem, it required the setting up of 24 separate rigid surfaces for the crimping, and an additional rigid surface to the catheter. But there's only two deformable bodies, the vessel and the stent, in the entire model. Now again, for this analysis, I found that the different stages of the crimping and expansion require different contact parameters to work efficiently. So for the crimping and expansion phases, I used a contact separation force of 0.005. The contact separation force is the force that's necessary to pull apart two bodies in contact. So here, this is the force necessary to pull the nodes, or for the nodes to move relative to the crimping surfaces. For the release step, I found I had to reduce the contact force quite down to 0.0002. Now, that's more than an order of magnitude smaller than before, but I found that was necessary to get smooth release. You may ask why I simply didn't use this for the entire problem. Well, the smaller contact separation force makes requires the problem to solve much more accurately. It requires significantly more simulation cycles to resolve accuracy. That wasn't necessary for the crimping and expansion steps, and it would simply have resulted in the simulation taking significantly longer to run. But because I could use because this problem can be split into multiple load cases, each of these steps here requires a separate load case in Marc, and Marc allows you to change the contact parameters between load cases or between restarts of the problem. See, also between the crimping release and the catheter expansion, they had to revise the contact table to take the crimping surfaces out completely. So Marc gives you the flexibility to significantly change the contact parameters or how the contacts are used over the length of a complex simulation. All right, I think we have, sorry about the delay there for the audio problem, but to